Let's look a little bit more at the aerosol impacts. Here, not necessarily just intraseasonal timescales or MISOs directly, but changes in the short time scale which fit into intraseasonal time scales. So on a seasonal time scale, trend time scales, we mentioned aerosols and solar dimming as reducing the land-ocean thermal contrast, potentially explaining the decrease in monsoon seasonal totals over the last several decades, with a question about whether it's been recovering in the last 2 decades. So 1950s to 1990s, there was about a 10% reduction, and since then there is an argument that it is increasing, but actually the IMD data doesn't necessarily show that. So if you go to my podcast on monsoon extremes, you will see some discussion on that. The other discussion we already had is also the direct and indirect effects of aerosols on monsoon processes and potentially on MISOs and rainfall. I will point to 2 studies here that make contrasting or contradicting points about how aerosols affect the monsoon rainfall at short time scales. This is from one group which looked at the climatological mean of the aerosol optical depth, the cloud fraction, and daily rainfall, and they argue that the associations of daily rainfall, precipitation rate, cloud fraction, cloud top pressure, and cloud top temperature with aerosol optical depth lead to conclusion that aerosols can actually increase the rainfall and total daily rainfall and precipitation rates. So here you are seeing aerosol optical depth increasing the rainfall, daily rainfall, as well as precipitation rates, and they relate that to basically a cloud fraction and cloud top pressure and temperature. So cloud top pressure is decreasing. Be careful about the scale here. It's decreasing, going up, and the cloud top temperatures decrease. And this paper argues that basically aerosol impact is to deepen the clouds, and then they use a model to do microphysics to argue that this kind of change in cloud properties, cloud top temperatures, the reflection of the solar radiation and the cooling, etc., lead to changes in the hydrometeorology, so ice particles forming and effectively increasing the rainfall at the fast time scales that at which the aerosols act, which would fit into the active break periods, and that would give you different conclusions than the following paper, which is another group which then divided the aerosol loading into high aerosol periods and low aerosol periods, like we had seen already, where the high and low aerosols were used to look at heating and the circulation anomalies, the concentrating effect of the circulation anomalies, increasing the land-ocean contrast and affecting the transition from break to active periods and the amount of rain in the active period. The arguments here about the high and low aerosol periods is to look at these kind of aerosol loading and precipitation, and there is a lag in which these are composited. But the argument in this paper is that the aerosol, especially high aerosol periods, are affecting the stability in the atmosphere and the cloud droplet sizes as well, cloud droplet effective radius, and are actually reducing the rainfall in the periods that are in fact affecting the break and active periods and their intensities. Okay, so this is showing here for different years, 2004, 5, and 9. and looking at different lag periods between aerosol optical depth and precipitation, and arguing that the precipitation is in fact reduced by high aerosol loading. And they also show figures of aerosol optical depth and lapse rates and at different lags, so lag 5 days, lag 1 day, and here no causality is inferred. And here we are looking at again, so these are absorbing aerosol indices and looking at lapse rates and cloud droplet effective radius. So A here is corresponding to year 2004, 5, and 9. So you can see that 2004, 5, and 9, looking at lapse rates of the total aerosol optical depth, absorbing aerosol index, and cloud droplet effective radius. And the conclusions on the cloud droplet effective radius is different here than here and here. So here no causality is inferred. Here there is a lag of 5 days with which CDR is affected, and here there is no causality. In other words, both these papers are invoking both the thermodynamic effect in terms of the lapse rates or cloud structures, cloud top temperatures and pressures, and also invoking microphysics in terms of either the hydrometeorology and precipitation rates or cloud droplet effective radius and precipitation rates, but coming to completely opposite conclusions about whether rainfall is increased or decreased by aerosols. I wanted to mention that basically because the aerosol story is quite complicated, and it is also related to intraseasonal timescales through these mechanisms that we looked at the mean monsoon changes before, where we said the aerosol loading and the related heating in the northwest cross corner of the Arabian Sea actually increases the heating contrast similar to the Tibetan Plateau heating here, and intensify the low-level jet and the moisture convergence. And in this paper by Vinoj et al., the conclusion is that depending on whether it's sea salt or the dust, and whether it's the total rainfall or the stratiform rainfall, the change in precipitation shown here can be different. So sea salt is reducing the total rainfall and the stratiform rainfall, whereas this is the lag of 6 days. So we are still talking about rainfall intensification on very short periods which fit into active and break periods, so not necessarily classifying them into active and break periods, but to the extent that monsoon has an intrinsic time scale of active and break periods, and rainfall rates are much higher in the active periods compared to the break periods, we are looking at total rainfall changes, daily rainfall changes here. So you can see that the total dust is changing the total rainfall and stratiform rainfall in terms of increasing it, whereas sea salt is decreasing it both for the total and stratiform. So again, another conclusion that is not related to dust or aerosol loading on the subcontinent, but forcing from the Arabian heat low and Arabian dust loading region. So I wanted to include that just to show that the aerosol story remains to be fully resolved, but it seems quite certain that aerosols are affecting the mean monsoon via solar dimming kind of processes, land-ocean thermal contrast, and they are affecting high frequency rainfall, daily rainfall rates, which go into active and break period timescales. And they're acting through thermodynamic effect like lapse rates and microphysics impacts through cloud droplet sizes, cloud structure, and rain rates. Okay, so you can follow up with lots of other papers. This is one of the topics where increased understanding doesn't necessarily reduce the uncertainties, because there are issues of capturing the processes in the models as opposed to what are derived from observations and confirmed with high resolution models, either idealized microphysics models or high resolution regional models. How do the global models do these? That has to be still resolved. So aerosol is a tough topic, but for the interseasonal timescale variability and predictions and the distribution of active and break periods and rain rates within them and transition from break to active phases, especially considering that the predictability of the break periods seems to be higher based on some of the studies that have reported the separation between predictability of the active and break periods. So lots of problems there that are all interrelated, lots of challenges, difficult problems.